Let me introduce the next speaker, Adriana Simona Mihaita from Australia. She will speak on the integrating mesoscopic traffic simulation model and simplified NO2 estimation model.
Yep. All right.
Okay. Could you please start?
Yes. Good morning, ladies and gentlemen, and welcome to my presentation. My name is Simona Mihaita, and I'm currently working as a researcher in Data 61, affiliated research unit of CSIRO. But the work I'm presenting today is the work that I did before coming last year to Data 61, which is in Nancy from France. It's about integrating a mesoscopic traffic simulation model and a simplified nitrogen dioxide estimation model in order to predict the impact of air pollution. And so the main motivation for doing this type of studies is that, well, very soon, actually, United Nations predicted that by 2050, almost 70% of the world population will live in cities. And we already know that 61% of the total emissions of carbon monoxide are produced by highway vehicles. And whether you believe it or not, a lot of the pollutants that are currently in the air are mainly produced by road transportation. Congestion plays a very important role in our life, and therefore, for example, 56% of the nitrogen dioxide in the air is caused by traffic congestion. Of course, I'm not talking about the economical and large impact, the costs that we actually get from air pollution. So the main challenge, I think, for everyone working in transportation system is to be able to propose new traffic management strategies that would actually help our life, not only in terms of mobility. Everybody's talking, okay, I want to go there faster, I want to improve my daily travel and so on. But what about our health? How are we improving our air quality? So my presentation today is going to introduce you the context of my previous work, and then I'm going to talk about how we build this integrated traffic and air pollution simulation model, the framework, the data we had, the simulation model, and the nitrogen dioxide regression model, together in the end with the validation and the seasonability study. So in Nancy, the main project we had was called Lorraine Smart Cities Living Lab. Now, this project was focused on two main concepts, which are very important, and the European Union insists a lot nowadays on so that new cities take into consideration the concept of eco-conception and eco-innovation. Now, what is that? So when you say eco-conception, you really want to think about methods to reduce the impact of urban reconfiguration. You need to be able to make decisions so that you will have sustainable cities in the future. When we talk about eco-innovation, it means that we want to be able to find solutions and integrate new green technologies in the city that will help our life and live healthy in our sustainable cities in the future. And the most important worry for Europe nowadays is to be able to integrate the citizens and make them a living part of this whole ecosystem, if you like, become active and become aware of that the things that they do impact the others and, of course, their own life. So the main focus was on Nancy Grand Coeur Eco Neighborhood. So what is an eco neighborhood, right? There is this labelization method right now in France is very popular. Cities that want to improve, let's say, the mobility in certain neighborhoods, they apply for this labelization. Once they get it, they have to engage into a long-term modifying and restructural activity to really prove that the neighborhood they applied for is really becoming an eco-neighborhood. In this case, so what they want to do, they want to offer a good air quality for their citizens. They want to, of course, reduce the traffic congestion and improve the air quality and rethink all the mobility, make use of green technologies. So this is just a snapshot of the eco neighborhood. It has 15 hectares. It's not that big. 9 million travelers that pass through this neighborhood per month. It's not that big maybe in terms of other cities around the world, but still, for a city of this scale, it is quite a problem. These are just some examples that have already been implemented in the neighborhood. They already have electrical cars, reacher stops, public bikes. They have the carpooling system. And lately, before I left France, they were using the mobility platforms, which were meant to help citizens have real-time information about the public transport and so on. So this was already in place. Now, we have started to work on traffic-related problems. We already did a lot of traffic signal control optimization for them, but this part of the work was focused in to be able to simulate the traffic behavior, but also include the impact that this might have on the air quality inside the neighborhood in one simulation model. And of course, to be able to integrate heterogeneous data sources that we received. So, for example, the central traffic center was CUGN, and they gave us all the information, the traffic volumes, the network configuration, the traffic signals, and so on, so that we can build our traffic simulation models. And the air quality monitoring station, which was Air Lorraine, gave us, for example, the nitrogen dioxide emissions. They had fixed stations in the city, and also meteorological data. These were the available data sets that we had. And together with these data sets, we tried to build our integrated model. Now, I'm going to talk about the framework, the data we had, and the challenges, of course, for meeting their requirements. As you can see, so this is the projection of the neighborhoods and how they want to transform it in the future. This is the current state of the neighborhoods in 2013. And our focus only for this particular study was on this big boulevard over here, which was near the train station, as you can see. Why did we choose this area? Simply because here it's the air quality monitoring station from Air Lorraine, which provided for us like accurate information about the pollution concentrations in the city. So we had like a very reliable source of information in terms of air quality, so that we can compare our results. So what we did, so we took all the traffic data collection that we had, so the network, the vehicle dynamics, and so on, and together with all the emission data that they gave us to us, and the meteorological data, all together in one built-in mesoscopic traffic simulation model. We have done that in FlexSim, simply because it's a 3D simulation model, and we have been using it for testing the traffic signal optimization method that we did, and they appreciate it very much. After that, we have built the prediction model for the emissions and at the end validation. So for this study, I'm only going to present the nitrogen dioxide prediction model. It was the first one we started with, and before I left. So when we looked at the data that we received, I would like to say that we got one full continuous month of data. At that time, we couldn't have we would have liked to have at least 6 months of data, but that was not possible. But at least we got one full month of continuous data. It was January 2015. So this is the 24-hour profile of the nitrogen dioxide evolution throughout this month. And this is the number of cars evolution during this month. Now, if you look at the two graphs, you would see that during the AM and the morning and afternoon peaks, you have like an increased level of NO2 in the city, and definitely you can see as well that the number of cars, which is absolutely normal during these peaks, is also very, very big. So you would look at the two graphs and you would say, okay, yeah, good. So this means that whenever you have a lot of cars, the NO2 level will just go up, right? No, it's not that easy, not at all. And I'm going to explain why. There are other factors that can influence this and can be very problematic. If you look at the evolution throughout the whole month of NO2, so for example, and this is the number of cars throughout the month. So here was Monday. The yellow bar stripes are weekends. So you would see here that on Monday, the number of cars increases on the boulevard. Therefore, the concentration of NO2 goes up. Oh, all right, it's normal, right? We know that cars produce and will actually influence a lot the NO2. So when the weekend comes, you can definitely see that the number of cars drops, and as well, the NO2 level drops as well. Perfect. You say it's normal. But this does not happen the same on the third weekend. Although the number of cars drops, the NO2 level still goes up. And this can be like influenced by other factors that we really wanted to know, okay, what is influencing the NO2 level evolution? So we started to look as well the temperature, the humidity, and the wind, because were available data sets that we had. And for example, if you look at the humidity, so these are normalized values just for making it more easy to compare because they have different scales. So if you look at the humidity, mostly when in this particular day, let's say the humidity was high and the NO2 level was down, and as well the wind has a peak. So we had humidity, therefore rain and wind. So the NO2 levels were very low, right? And we can see, although we had a big number of cars on the street, still the NO2 level was low, simply because the precipitations, the rain and the wind help the NO2 concentration to just disperse and not accumulate. Whenever you don't have any wind and so on, you will just high air pollution in the city. So, all right, it was really, we know we had this complex problem, and we started to do some correlations in between all these factors that we started to analyze. So it was definitely, so between the number of cars on the boulevard and the NO2 level, we could see we have a loose Spearman correlation. This really indicated that there are definitely other factors that are playing a very important role, and we can see that the temperature and wind are very highly correlated, and also the fact that the temperature and wind have a negative Spearman correlation with the NO2 levels. All of this played a very important role, so we knew that if we want to have a good prediction, we would need to take this into consideration. So we then started to build our traffic simulation model. So what you see here, this is a 3D image of our boulevard near the train station, and it also contains tram stops mixed with normal traffic. We imported all the data that we had into the model, and then we implemented all the tram stops. Also, we had pedestrians in the model, so everything integrated all together with all the data that we had. At the end, we basically ran the model and we compared it with manual checks in the city, simply because it was very possible to do that. We didn't have like a big simulation, and we could validate our results very easily. So once we had the simulation model, we said, okay, good, we have this, but okay, we want to visualize. So as the 3D simulation runs, we want to visualize as well the NO2 level and the dispersion in the city. So what we did, we integrated the emissions, the NO2 emissions. We integrated them as discrete entities, as you can see here. So when the model runs, we would see like clouds accumulating over the neighborhood. But not only, all the weather and all the other statistics we had, we integrated as well to run together with the traffic simulation in the same time, so we could have like the same monitoring in the same model. So okay, we did that. So it was interesting to see, but we still wanted to answer our question: what is the role that the number of cars plays on the NO2 level? So what we did, we applied a least squares multiple regression model of NO2. We trained the model on the first 20 days of data that we had, so all the available data sets, and then we conducted a regression analysis and the tendency and seasonality analysis, and at the end we predicted the NO2 concentration on the last 10 days of January. So when we did that, this is what we obtained, mostly the relation between the NO2 and the factors that we considered. So you would say, okay, these are your predictors. So, okay, what about them? So if you look at the variance inflation vector, which is a factor indicated if the predictors are correlated in between them. So basically, if this factor is less than 5, then that means that your predictors are okay. They are not correlated in between them, so you can just you can be confident that they will not influence. So we were confident about that. But then, so we also had this p-value measure that you can see here. And this one determines the appropriateness of rejecting the null hypothesis when you have a hypothesis test. It goes from 0 to 1. And if it's superior to 0.5, it means that your predictor doesn't influence your NO2 level that you're trying to predict. So for future studies, we knew that humidity, okay, we know it plays a role, but it's not extremely important, yes. So I'm just gonna stop my presentation by talking about the validation. So we used the mean absolute percentage error, which is 23.61, and normally the studies indicate it should be inferior to 30% to validate your prediction, which indeed happened. And the last thing we did trend and seasonality analysis, because as you saw, the number of cars tends to follow the same trend during the day. During the morning peak hours, goes up, then goes down, and again in the afternoon. So we wanted as well to include that in our prediction. So what we did, we predicted the traffic volume for the last 10 days. The best results were given by the multiplicative model, which gave us MIP for 21. We inserted again in the prediction model, and still at the end, we got an MIP of 25, which is still good. It's worse than the first time, of course, because when you predict once again the number of cars, yes, it deteriorates, but still it's inferior to 30%, and this was for us encouraging. So future conclusions, they have continued with the project, and the main focus was to be able to use and encourage citizens to use mobile sensors in the city when they are traversing the eco-neighborhood, that they collect data and they want to measure in real time the NO2, SO2 levels and so on. So they are working on that, and they have already conducted various tests. I'm looking further for the results that could further element this type of simulations or model in the future. So thank you, and sorry if I...
Thank you very much.